What is the maximum value of force F such that the block shown in the arrangement does not move? Take G is equal to 10 meters per second square. Here we have a block. A force F is acting in this block in this direction, that is 60 degree with the horizontal axis. We need to find the maximum value of F such that the block is still not moving. So here we have the information, the mass of the block is square root of 3 kilogram, and the coefficient of friction between the block and the surface, surface of the table is mu is equal to 1 by 2 square root of 3. So here we need to find the maximum force that we can apply so that the block is still staying there, that is without moving the block. First, let us consider what we need for vertical equilibrium of this block. For vertical equilibrium of this block, that is the block needs to stay in the surface of the table without moving up or downwards. That is, we call it vertical equilibrium. In this case, we know that if we draw a free body diagram, the block will have vertically, it will have forces acting on it is the mass of the block and the gravity, right? Then it has a normal force which is R, which is acting against the mg, and we have a force acting on this direction, right? That is on 60 degree to horizontal to the block. So these are the three forces that is acting on this block. So in the case of vertical equilibrium, we can write that the normal force R must be equal to the mass times gravity of the block plus here the sine component. So that is the vertical component of the force, the sine component F sine 60. So that is the condition for vertical equilibrium. We know that m is square root of 3 times g plus F is we know sine 60 is square root of 3 by 2. So that is square root of 3, square root of 3 divided by 2 times F. That is the normal force on the block for vertical equilibrium. And we know that if the block should stay without moving, when we are applying a force, then the force, that is the friction, the force with consideration of friction should be, that is the resultant force should be greater than F cos 60. That is the vertical, sorry, the horizontal component of the force. Here F mu is the resultant force experienced by the block. Or, sorry, this is the force that we are applying, and F mu is the force that we need to apply to move the block, that is against the friction, friction and the mass of the block. So in this case, we know that the force of friction F mu has an expression. F mu is equal to coefficient of friction times the normal force, that is mu r. So according to this equation, let's call this equation 1 can be written as mu r must be greater than or equal to the applied force F times cos 60 is 1 by 2, right? That is F by 2. And we have the value for R here. So let us substitute the value for R into this equation. So what we will get is mu times R square root of 3g plus square root of 3 by 2 F must be greater than or equal to, for the block to be stable there or not moving on the surface. We know that mu is 1 by 2 square root of 3. 1 by 2 square root of 3 times square root of 3g plus square root of 3 by 2 F. That is, should be greater than or equal to F by 2. By rearranging this equation, we can take this part 1 by 2 square root of 3 inside the bracket. So what we will get is g divided by 2 plus F by 4 should be greater than or equal to F by 2. Let us take this part F by 4 to the right hand side. Then we will get g by 2 should be greater than or is equal to F by 4. So here we can define the force which needs to be applied to just move the block as F. So F is equal to, or F is, yes, F must be, let's take this 4 to this part to the left hand side. So F should be either less than or equal to 2g. So this is the force, or F is equal to 20 Newton. So this is the force, the maximum force that we can apply to this block without moving it. So if we apply a force higher than 20 Newton, that block will start moving.